Okay, Assalamualaikum warahmatullahi wabarakatuh. Now I will talk about the different breakdown mechanisms. So, as introduced in the class, we have two types of breakdown mechanisms, which are the Zener breakdown and also the Avalanche breakdown. Okay, so now let's look in detail for each one. So let's look at Zener breakdown first. Zener breakdown occur for PN junction with high doping. This is important. That's one of the characteristics. Avalanche breakdown occurs for normal doping. So, and the process both will give a breakdown is sudden rush of current in reverse bias after a certain voltage. So the voltage where the breakdown occurs is called the breakdown voltage. Now let's look at the Zener breakdown. Zener, one characteristic of the Zener breakdown is you can create Zener diode where you know exactly, you can design exactly the breakdown voltage. But for the Avalanche is it can vary, so it's very difficult to design. It's more accurate to have a specific breakdown voltage with the Zener. Okay, now let's explain how Zener breakdown occurs. So both breakdown only occurs in reverse bias. So let's say this is your P. I'm drawing the PN junction. Energy band diagram is P. Then you know it's reverse bias. So it should be like that. And then you have your N. This is the N side, right? P and N, the Fermi level of the N is closer to the conduction band. This is EC, EV, EC, EV. So what happens here is that for Zener breakdown, because the high doping, sometimes they could degenerate. The Fermi level can go with the inside the conduction and the valence band. So if I draw a true Zener diode, you have the Fermi level inside this, what you call it, inside the conduction band and the valence band. So what happens is when this occur, right, what happens is you can see normal for reverse bias, you won't see much of drift current. Drift current is due for the minority electrons drifting from P to N, and minority electron here drifting from N to P. But for Zener breakdown, when you have a lot of doping like here, like this, what happens is that here remember I told you in the valence band you have lots of electron, but it's bound. For N in the so for here for the N at the conduction band, there are lots of hole, but it's bound. But if it's the dope is very high, what happens is the electron here sees the whenever for electron to be free, the electron need to be able to go to the conduction band. So what happens in Zener breakdown, tunneling occurs. So the key word here is tunneling. Tunnel. So what happens in the electron, the bound electron here tunnels through the band gap and goes to the conduction band. So if you have a lot of electron tunneling, it's because you know that in the valence band you have a lot of electrons but bound. So this electron somehow see like a shortcut, like it can tunnel through the band gap, goes to the other side of the conduction band and then freely move and being collected, and that's how you suddenly get a lot of current due to the tunneling process. But so that's for Zener. Now let's look for Avalanche. Avalanche normally occur normal doping and normally at very high voltage or electric field. electric field. So what happens is, if I draw the apa nama ni, energy band diagram. So I started with the P here, and remember it's at high voltage. So if I go, so I need to draw a little bit extreme here, and it goes like that. Okay, so this is your P color. So this is the P, this is the N. Okay, so the formula for the P is there. So doping is not too high, it's not degenerate. So for the Zener, you can see the formula level is inside the conduction and the valence band. Here is still inside the band gap. So what happens is, for avalanche breakdown to occur, you apply a very high field, right? You can see the hill is very high, the potential is very high over here. So what happens is, previously in normal reverse bias, you will see some electron will be able to drift, right? So this minority electron will drift, minority hole will also drift upwards, right? So that's how we understand in reverse bias. But at very high field like this, what happens is that the electron, when it's drifting downwards, you can imagine like electron like a ball, right? When it's drifting at very steep hill like this, it will change from potential to high potential to high kinetic energy. So this electron will travel very fast. So it will hit the atom, and what happens is one electron will create one electron hole pair. So this electron will move very fast and it will hit the atom, right? So this electron will be very fast and hit another atom and transfer this energy to the atom, and this will release, this energy will be gained by the electron to release one electron hole, one hole. So if you started with one electron here, then if the electron hits the atom and release electron hole pair, this process is called impact ionization. So the keyword for avalanche process is impact ionization. So impact ionization is a process where the electron impact to the atom and ionize and release electron hole pair. And this electron will again hit another atom and release another electron hole pair. So remember, electron to be moved freely is be in this overall region. Here is the conduction band, here is the valence band. So for a hole to move, it need to be in the in the valence band. So you can see every time it hits, it will give out one electron hole, and this further can hit and give one electron and one hole. This hole can also hit the atom and release one electron and one hole. So if this process occur, it's similar to the, if you remember in in nuclear reactor, I can't remember whether it's fusion or fission. It's either one. So it's similar nuclear chain reaction. It's like a chain reaction. So one electron will hit atom and then will release electron hole pair. Another electron will hit another atom and will create another electron hole pair. So you can imagine in a very short time, you have suddenly a lot of free carriers here due to impact ionization, and suddenly that's how breakdown occur. When you have a lot of free carriers moving and being collected here, hole will be collected to the P, the electron will be collected at the end, and suddenly you see a lot of current. So that's how the mechanism occur. And the name avalanche, if you look at through here, when the electrons travel and impact ionize, it's like an avalanche. Maybe you can Google for avalanche video. Avalanche normally occur in ski, and when you do the snow, when you ski in the snow at the mountain, you have avalanche. So it's similar. The name is taken from that process where one electron can actually impact ionizers and do chain reaction. Suddenly you get lots of current. So that's the two main breakdown mechanism. You have the Zener breakdown and the Avalanche. Zener is high doping, and the keyword is the tunneling across the band gap, and Avalanche is normal doping but it occurs at very high voltage because you need the high potential to create a high kinetic energy to have the impact ionization. And when impact ionization occur, in the end you have lots of current, and that's the breakdown. Okay, that's all for the breakdown mechanism. If you don't understand, you can always come and ask me. All right, thank you.